Hello everyone and welcome to the class of hydrocarbons. Today we will be taking a look into the aspect of the aromatic compounds. So when I am speaking about the aromatic compounds, that is nothing more than the aromatic hydrocarbons. Okay, now what exactly are these aromatic hydrocarbons? These hydrocarbon compounds are usually cyclic compounds, a specialized cyclic compounds which has a unique smell or an unique odor, you can say. Now, because of these odors, these set of compounds are also called as arenes. Okay, so these particular aromatic hydrocarbons are nothing more than these are specialized cyclic compounds, right? What is the unique character that we have said about this is these particular set of compounds are going to have a unique smell. Okay, so due to this unique smell, okay, due to the presence of unique smell, these particular compounds are also called as arenes. Now basically we categorize these hydrocarbons into two classes based on its derivatives, benzenoid and non-benzenoid. So our studies are going to be strictly restricted to the benzenoid type of compounds. Okay, so when I am speaking over here about the benzenoid, okay, that means we are going to have the compounds which are derived from benzene. Okay, right? So any particular cyclic compound which is derived from benzene, or it looks like a benzene, we classify that under the benzenoid system. Okay, so for example, benzene itself, we will take starting point, we will start with a benzene. Okay, so we have benzene. Okay, now let's fuse these two. So this one over here becomes as naphthalene. Okay, you can also go for the next version, that will be an anthracene. Okay, I would like to take another one over here, something like this. Now these over here are the biphenyls. Okay, all of these kind of systems which are derived from the benzene falls under the category of the benzenoid type of compounds. Okay, now how to name these particular systems? We'll start our nomenclature for the simple monosubstituted compounds. Now why am I speaking about the monosubstituted compounds? Is because when you take a look into a benzene, okay, now in the benzene what happens is these are your carbons over here. How many carbons do we have? We have 6 carbons, right? Now these 6 carbons, what we have, each of them is attached to a single hydrogen like these, correct? Now what happens here is all these hydrogens are same, okay, same in their nature. So therefore whenever we take a look into its monosubstitution, that is, you are going to replace only one out of these particular hydrogens. Let's say we are going to substitute this, we are going to replace this hydrogen by some group, let's say an electrophile. Okay, so when it happens, it is going to give rise to only one type of compound. Okay, only one type of product is going to be obtained. Okay, due to which the naming becomes easier for this one. Okay, but we substitute further, that is for the dye substitutions. So when you go for the dye substitutions, you will see that you can get 3 different types of products. Okay, so either it is going to be as, let's say, this is a position which is been substituted by our electrophile there, and the another position that is going to be substituted, let's take this. This particular position we call it as ortho. The particular position adjacent to the one substitution is called as an ortho position, right? So this is the first type of product what we observe upon dye substitution. Correct. What we have done, we have replaced one more hydrogen by electrophile. Okay. Now I can also replace this particular, that is a meta position, the hydrogen at the meta position, by an electrophile. Correct. So that time I will receive my second type of product. So that particular product is going to be as, here is one electrophile, here is one electrophile. I am not representing the hydrogens now. Okay. So the third type, the third possibility is that we can replace this particular, that is at the para position, the hydrogen at the para position, by an electrophile. So we are anyhow here getting 3 different types of product. So 3 different types of product is obtained upon dye substitution, while only one type of product is obtained upon molar substitution, right? So now the first case. In the first case, this is going to be as 1,2 dye substituted product, because this is position 1, this is position 2. Okay, so this one is going to become as 1, 2, 3. So it is going to be as 1,3 dye substituted product. Similarly, this one is going to be as 1, 2, 3, 4 at the position 4. So therefore, this is going to be as 1,4 dye substituted product. Right? So if we take one example over here for the mono substitution, let's take one example for mono substitution, something like this. Mono substitutions, in a sense, we are going to replace or substitute only one hydrogen by some other group. Let's say that I am going to place over here CH3. So this particular molecule is nothing more than toluene. Okay. Or also we can call it as the methyl benzene. Okay, this is a high name, that's a methyl benzene. When we have taken a look over here as 3 different products for dye substitution, let us take the examples. So for the dye substitutions, let's take the same way as what we have for the methyl benzene. Okay. So we will replace one hydrogen again by the methyl group over here. So what we are going to get? CH3 and CH3 again, right? So now this is nothing more than 1,2 dimethyl benzene. Okay. It is also called as ortho, because the substitution is at the ortho positions. Okay, so it is also called as an ortho, and this molecule is called as orthoxylene. Okay, now what shall we do? We will go with the second one. So one methyl group will be here, another methyl group will be over here. Okay, so CH3. Another CH3 over here. Correct. So this one will become as 1,3 dimethyl benzene. Okay. So this one, it is, the substitution is at the meta position. So M xylene. That is the meta-xylene. Okay. Let's go with the last one. The last one, let's represent it over here. CH3, CH3, right? So now, what is going to happen over here? 1, 2, 3, 4. So 1,4 dimethyl. Okay, dimethyl benzene. Now, quite simple. It was an orthoxylene. This was a metaxylene. This position is the para. The position occupied by methyl group is para over here, right? So it becomes as, of course, paraxylene. Okay, the common names are quite important sometimes. Paraxylene. Okay, let's keep this aside. So this was all about how do we name a monosubstituted system and of course the disubstituted. You can also go with like chlorines. Okay, 1, 2 dichloro. If you substitute with bromine, it becomes as 1, 2 dibromo benzene. Correct. So depending upon what group you are attaching and what are the positions, those particular, whenever you represent the positions, the name becomes as an IPAC. Okay, the name is IPAC system. While if you represent ortho, meta and para position names, that time the naming becomes a common type of name. Okay, so this was the difference. Okay, so let's observe the next category. We'll start our next section in order to determine the particular compound whether it is aromatic or not. Okay, so if you have a particular compound and if you are in a flux as to understand whether this particular compound given is aromatic or not. So, for a compound, to be aromatic, okay, to be aromatic, it has to follow the 3 rules. Okay, the first rule is that the compound should be cyclic. First thing is, whatever the compound that you are looking at, if you want it to be aromatic, then what is our first condition? The compound should be cyclic and planar. Okay, so this is our first point where we need to observe it carefully, whether the given compound is cyclic and planar. In this particular given compound, whether this particular given compound is a conjugated, that means the second requirement is the conjugated system. That is a system either with a double bond or with a double bond with some positive charge or negative charge in such a way that the particular pi electrons keeps on delocalizing. Okay, so that is where we call it as a conjugated system. Okay, so that is a condition. And the third condition is very, very important, and that is going to be the Higgins rule. Okay, so it has to follow the Higgins rule. So these are the 3 points. Now, question is, what exactly is the Higgins rule here? So the Higgins rule is nothing more than a particular statement which you can apply directly in order to understand whether the compound is aromatic or not. It directly says that the number of pi electrons, very important, in a given system should be equal to 4n plus 2. Okay, if it satisfies this condition, very important condition, if it satisfies this condition, finished, your compound is aromatic. Okay, so n is equal to 0, 1, 2, 3, so on and so forth. Let's apply this. Let's try to understand it. Okay, so first one, let me take one example over here that is going to be of cyclopropene cation. Okay, let's take this particular example. Please observe that we have a double bond over here and a positive charge over here. Right? Now, due to the positive charge, what can happen? This particular double bond can shift between these positions and these positions. So it keeps on, yes, it keeps on delocalizing. Correct? So therefore, let's take this particular thing and observe. Can I apply the first rule? That is, the compound should be cyclic. Yes, it is cyclic. It should be planar. It is a planar. It has a conjugated system. Now let's apply Higgins rule. Okay, so what does the Higgins rule says? the number of pi electrons. Okay, the number of pi electrons should be equal to 4n plus 2. Okay, now how many electrons do we have? Pi electrons here. We have one pi bond, that means 2 electrons. Correct. Now, number of pi electrons can be equal to this particular sum provided n becomes 0. Okay, so in this case, in this particular case, n is equal to 0. If n becomes equal to 0, that means pi electrons is equal to 4 into 0 plus of 2. Correct. So pi electrons are 2, and therefore this given system, yes, it is aromatic in its formula. Okay, now let's go with the next one. Let's observe with respect to a simple benzene. We know already that this particular benzene is aromatic. Okay, let's prove it with respect to the Higgins rule. Now, according to the Higgins rule, the number of pi electrons, okay, is equal to 4n plus 2. It should give this particular thing. So, number of electrons, that is number of pi electrons. Now, observe 1, 2, 3. So, therefore, what I have over here is the 3 double bond means there are 6 pi electrons. 1 double bond, 2 electrons. Correct. So, 2 plus 2 plus 2. There are 6 pi electrons here. And it can be equal to this provided in this particular case n is equal to 1. If this thing occurs, then 4 into 1 plus 2. The number of pi electrons are 6. Therefore, it is occurring as per as the Higgins rule. Correct. We'll observe one more. Let's take into consideration of this compound here. Okay. So observe carefully. This is cyclopent dienyl. Okay. Cyclopent. That means a 5-membered cyclic system. Pent, 5. Correct. Di means 2. E, double bonds. Dienyl. Why did I write that? Dienyl is because this particular system is charged. Okay, so therefore dienyl and iron. Because it is negatively charged, I will take it into consideration as an ion. Now, in order to prove its aromaticity, here try to understand these are the extra electrons. These electrons are involved in delocalizations. So it behaves as a pi electron itself. So therefore, if I take over here, 4n plus 2 is equal to number of pi electrons. Okay, so how many do we have? 1, 2, that means 4 pi electrons. Okay, 4 pi electrons and 5 and 6. So even these 2 electrons I am taking from the charge. Okay, so total number of pi electrons I can conclude as 6. So therefore, n is equal to 1 even in this case. So 4 into 1 plus 2, that is 6 pi electrons. Quite simple, right? Now, let's go with the next one. Let's take this system into consideration. 1, 2, 3, 4, 5, 6. So, okay. Right. So let's take this particular system into consideration and let us say positive charge 1, 2, 3. This is cyclohept 1, 2, 3, 4, 5, 6, 7. Correct. So cyclohept 1, 2, 3. There are 3 double bonds now. So therefore it becomes as cyclohept triennial. Okay, so cyclohept triennial cation. Okay, so now in this case, what will happen? 4n plus 2 is equal to number of pi electrons. Okay, so 1, 2, 3, 4, 5, 6. 6 again, therefore n is equal to 1. So 4 plus 2, now again 6 pi electrons. Therefore, even this one is aromatic. So all these 4 are behaving as per as the Higgins rule. Therefore, all these 4 are going to be aromatic in their characters. Okay, so that is quite simple as that. Let us take one example here. Okay, now if I take this into consideration, okay, 1, 2, 3, 4, right? So 1, 2, 3, 4, 5, 6, 7, and 8. 8 carbon systems. Now this one is cyclic, it is planar. Okay, so our first thing is done. It has double bonds which keeps on rotating. Yes, conjugated system. Does it behave as per as the Higgins rule? Now that is a concern. Now therefore, when we have 4n plus 2 is equal to pi electrons. Okay, so 1, 2, 3, 4, 5, 6, 7 and 8. There should be 8 electrons, 8 pi electrons. Any substitution would give me as 8 pi electrons here. If I insert 0, it will give me 2 pi electrons. If I insert 1, as n is equal to 1, it is going to give me 6. If I am going to insert as n is equal to 2, it is going to give me 10 pi electrons. So here the Higgins rule is not applicable in the cyclooctatetraene. Okay, so here this system is a non-aromatic in the character. Okay, so that is all about the aromaticity. This is how we predict about the aromaticity. I hope you have understood this all. To take care, we'll meet you in the next video.